Hello everyone, in this video I'm going to be talking about how to draw all possible constitutional or also called structural isomers for two different chemical formulas, C6H14 and C5H10. So let's start out with C6H14. So remember the constitutional isomers would have different connections. They would have different skeleton, different structure, but they would have obviously the same formula. Before you do anything on this, make sure you know what's going to be the degrees of unsaturation or an IHT on this compound. So remember the degrees of unsaturation or the IHD formula is typically 2 times the carbon plus 2 minus the number of hydrogens minus the number of halogens plus the number of nitrogens and divide that by 2. That's the formula you want to use to figure out the degrees of unsaturation or index of hydrogen deficiency. Um, this will tell you whether you could possibly have a ring or a pi bond. You mean most likely a double bond or triple bond. So that's why it's important to figure that out first. So for our compound, we have 6 carbons. So I'm just going to go ahead and write that down as 2 times 6 plus 2, that's a part of the formula, minus the number of hydrogens. So in this case, the number of hydrogens would be 14. We don't have any halogens, we don't have any nitrogen, so we can leave those alone. Divide that by 2. So this actually comes out to be 0. So that really means it's an saturated hydrocarbons with no ring, with no pi bonds. Obviously, pi bonds would be unsaturated hydrocarbons. Now I know this is just going to be an open chain structural isomers, and I can go ahead and start out with maybe in a simple one where all 6 carbons are going to be in a straight line. So something like that. And you want to make sure I'm going to go ahead and name those as well. I'm not really going to talk about the stereoisomers in this particular case, only the constitutional isomers. I'll have a separate video where I'll talk about the constitutional isomers and the stereoisomers possibilities. So the name for this one would be an hexane. Okay, now what I can do to draw another one. So this one has 6 carbons in the main chain. Maybe I can start writing the structural isomers with 5 carbons in the main chain now. So that's how you want to kind of shorten your chain. And when you shorten your chain, you want to have that 6th carbon somewhere else as a substituent on the main chain. So I can possibly have it right here. So that's one possible way of doing it. So that will still give you a formula of C6H14, but the name for this one would change. Remember, the name for structural isomers are going to be different, and that's how you know they are structural isomers, as long as they have the same chemical formula. So the name for this one should be, if I count it from the right side, that's 1, 2, 3, 4, and 5. That would be 2. And there is a methyl group on the 2nd carbon, so that's 2-methyl pentane. And then you want to think of what else could you do to maybe have a different connection and maybe have the same number of carbons in the main chain. And here we're starting out with 5, so maybe I can go ahead and draw another one of those and see what the possibility going to be. I can certainly have this methyl group that was on the 2nd carbon. Instead of on the 2nd carbon, I could have it on the 3rd carbon. So that would be now 3-methyl pentane. So that's still in the constitutional isomers. We just have a different connection. Now, what else you can do? Can you have another constitutional isomers with 5 carbons in the main chain? And it turns out no. Someone might think that what if you actually go ahead and to position a carbon right here, like a methyl group right there? Well, in that case, that particular compound would be the same as 2-methyl pentane. So you don't really want to do a duplicate because, in that case, it would start counting from the left side and your methyl group will be on the 2nd carbon. So that would be the same as 2-methyl pentane, which we already have drawn. So make sure you don't duplicate anything. Let's look at maybe the next possibility. So it seems like we've already done with the 5 carbons in the main chain. Maybe shorten the chain a little bit more. So instead of having it a 5, maybe have 4 now. So I'll go ahead and draw 4 carbons in the main chain. And then think of what is the possibility of getting the other 2 carbons as your substituents on this one. Maybe I can have it on the second carbon right here, and maybe on a third carbon right there, something like this. And in that particular case, I do get all 6 carbons I needed to have. And what would be the name for this? I can go ahead and call this, or number this way, 1, 2, 3, 4. If I number it from the right side, that would be the same as well. So that would be 2, 3 dimethyl, and in this case, it's going to be in a butane. Okay, that's another one. What else could you do to a 4 carbon chain? Let's just duplicate that right here. I could possibly have this methyl group that was on the second and the third carbon. Instead of having it on the adjacent carbon, what if they are on the same carbon? So something like maybe having it right here. So that's another possibility. And what would be the name for this? That's in a different connection, obviously. So that's in a constitutional isomer. That would be 2, comma 2, still going to be a dimethyl, and it's going to be in a butane. And is there anything we can do? We can't really do anything on the 4 carbon. If I, like, someone might think, what if I can just go and duplicate right here? And instead of having 2 methyl groups on this carbon, what if I have 2 methyl groups on this carbon? Well, it turns out that's actually going to be the same thing as your previous one, because in that case, when that happens, then you're not going to be counting them from the left side, but rather you're going to be counting those from the right side. So that's going to be 1, 2, 3, and 4. So now that's the same thing as the previous structure. So you don't want to be drawing that. You don't want to be doing any duplicates. So I'm going to go ahead and take that out. Can we have 3 carbons in the main chain? Well, we can try that. We have 3 carbons in the main chain, maybe something like that. So that gives you a number of 5 carbons so far. So that means I have to put the 6th one somewhere. And as soon as I put the 6th one somewhere, I can put it any one of those edges, either right here, right here, right here. And it doesn't really matter where you put it. Well, let's suppose if I put it right here, that actually gives you this compound as the same as this previous compound. So you can't really have any more constitutional isomers for this particular one. So that is going to be the number of 5 constitutional isomers for this particular chemical formula. As the chemical formula goes up, like if you have C7H14, then the number of isomers would also go up. And that's when it becomes difficult, because you're going to have to think of all the different possibilities. Let's do another example where we have C5H10 now. So let's see what's going to be happening to the C5H10. Like I said, I want to go ahead and first figure out what's going to be the index of hydrogen deficiency here. So that's going to be 2 times 5 plus 2, that's a part of the formula, minus the number of hydrogens here would be 10, and don't really have anything else going on, so divide that by 2. So that's going to give you 1 here when you do the math. So this 1 means that either you could possibly have 2 things. You can have a pi bond, which typically means a double bond, or you can also have a ring. You're not going to have both of them, but you can have one or the other. So that actually gives you different possibilities of these constitutional isomers. Anytime you have 1 degrees of saturation or 1 index of hydrogen deficiency, that gives you 1 ring or 1 pi bond. So maybe I'll start out with incorporating pi bonds in the main chain first. So let's say if I have 5 carbons in the main chain, so that's your 5 carbons in there. I cannot leave it like this, because right now the formula would be C5H12. You can count the number of hydrogens here because there's no double bond. Right now it's an alkane, so alkane would have 12 hydrogens in here. So what I really need to have here is obviously incorporate a pi bond somewhere. And when I'm incorporating a pi bond, I'm killing two of the hydrogens. And as a result, that will give you C5H10. Now I can have that anywhere. I can have it right here. Okay, so that's one possibility. I can also have that, let's say I'm going to duplicate down here. Instead of right here, I could also have it at this location. So that actually gives you two different positions for the pi bond. And when I'm counting my carbons in the main chain, I can count it from 1, 2, 3, 4, and 5. So that would have been, the suffix would be pent. And since we have alkene at the first position, you will call it 1-ene. So you could also call that as an pentene, because if the double bond position is at the first carbon, you don't really have to specify it. Then the second structure here is going to be the constitutional isomer, because the position of the double bond is different. So I can have it as 1 here when I'm counting it. 1, 2, 3, 4, and 5. So that would be pent 2-ene. You can also call that as a 2-pentene, so it's in the same thing. Now, what if you actually, what else you can do? Now, someone might think that I can actually go ahead and place the double bond right here. Well, if you place the double bond right here, then this structure actually is going to be the same as that, because as soon as you put the double bond there, I cannot count it from the right side anymore, because you want to make sure your double bond gets the lowest number in the counting. So in that case, I would have to count it from the left side. So that would have been 1, 2, 3, 4, and 5. So that is actually going to be the same as the previous one. However, this is not going to have any structural isomer. However, this could possibly have another stereoisomer. So this right now is like in a trans form or in an E form. You could have in a Z form of it, but like I said, I'm not really talking about the stereoisomers. In this case, only the constitutional isomers. But I would say here that you would have, one more stereoisomer. But remember, that's not really your constitutional isomer, so I'm not really going to draw that. What else you can do? Maybe you can kind of cut down the chain now and then see what's going to be the possibilities. So instead of having it 5 carbons in the main chain, have 4 carbons in the main chain, and start putting the methyl group somewhere on the chain as your substituent. So something like this. So that gives you 5 carbons, but remember, you still got to put the double bond somewhere, because you got to make it 10 carbons. So I can, in one possibility, I can put it right here. Okay. What else you can do? Uh, well, I can also put it right here. Okay. And I could also actually, if I use the same of this structure, instead of having a double bond right there, I could also have double bond right there. So that's another possibility. Is there anything else I can do? Well, someone might think that, okay, I'm going to go ahead and take that and have this double bond right here. But remember, this structure right here, and actually this structure right here is actually the same, because the position of the double bond is not changing, and the position of methyl is not changing. If it becomes hard to kind of look it down that way, number your carbon. So I'm going to go ahead when I'm starting from the left one here. So that's going to be 1, 2, 3, 4. Whenever you have a double bond and your substituents like methyl, ethyl, chloro, bromo, your double bond gets the priority, means you want to make sure your double bond gets the lowest number possible. Okay, so that's how the counting going to be for this guy. For the second one, the counting should be 1, 2, 3, 4. For the third one, I want to count from the right side again. 1, 2, 3, 4. Why I want to count it from the right side? That's because if I do count it from the left side, like this one, let me change the color here. 1, 2, 3, and 4. If I count it from the left side, then your double bond is getting the second position, but then your substituent, your methyl group, is getting the third position. But if I'm counting it from the right side, both the double bond and your substituent is getting the second position. So that's actually a better way of counting it. And then when you're looking at this last one, when I count this, that's going to be 1, 2, 3, 4. So that's actually the same as the previous one. So there is no point redrawing that. So I'm just going to go ahead and take that out. So what would be the name for this? For the left one, that would be, I have a methyl on the second carbon. So that's going to be 2 methyl. And I can just call this as 1 butene. And you don't necessarily have to specify the position of the double bond because it's at the first position. So you could also just call that as a 2-methyl butene. Now the next one would be, you would have 3-methyl. And again, their position of the double bond is at the first carbon, so you can just call that as a butene. And then this next one would be 2-methyl, and that would be 2-butene. You can call it like this. You got to specify the position of the double bond now. It's at the second carbon. And you can also call it like this. So you can call the but first, and then you can specify the location. So that would be 2, and then it would be an ene. So those are the possible ways I can think of that where your double bond can be placed. And these bottom ones wouldn't really have any other stereoisomers for this one. The only stereoisomers that would be possible was this guy right here. But then this is only when we have a pi bond. What if you actually have in a ring like we have talked about? Then let's talk about those possibilities. I could have just in a cyclopentane like this. So if you count the number of carbons and hydrogens, that would be C5H10. So that would be your cyclopentane here. Then I can start reducing the number of your carbons in the ring. So instead of having 5 carbons in the main ring, maybe have 4, something like this. It may not be stable one, but still we gotta just draw all the possible ones. So then I can have a metal just coming out from one of those positions. Now this one would be called as methyl cyclobutane. Then it doesn't matter where you put this methyl. I can put it right here, or I can put it right here, or right here. It still be called a methyl cyclobutane. Um, what else I can do? I can have maybe a 3-membered ring, something like this. And then now I gotta place 2 carbons or 2 methyl groups. I can start with putting both of those on the same carbon, something like this. So then I can call this as 1,1 dimethyl cyclopropane. Okay, that's one possibility. Now, whether I put these 2 methyls on this carbon or on this carbon or on this carbon, both of them together, it doesn't really matter. That would be the same constitutional isomer. Now, what else I can do? I could actually go ahead and start changing the position. So instead of having the methyl, both of the methyls on the same carbon, but have it maybe on one carbon and have another one on the other carbon, something like this. So the name for this one would be, I can start counting from any one of those carbons that is bearing the methyl group. So maybe 1, 2, 3. So that would be 1, 2 dimethyl cyclopropane. And that's the only thing I can really think of. You can't really do anything else. If you think that I want to put a methyl right here and right here, that will still be 1,2-dimethyl cyclopropane. I do want to mention that this guy right here, or this particular constitutional isomer, actually have two chiral centers. So I got a chiral center that's going to be right here, and a chiral center at right here. So since you have multiple chiral centers, you could have a total of 3 other isomers. You can have a maximum of 4, but one of them is going to be mesers, or 2 of them are going to be mesers, so 3 other stereoisomers are possible. So like I said, I'm not really talking about stereoisomers, I'm only talking about the constitutional isomers. I'll have another video where I'll talk about the stereoisomers possibilities. But for right now, this is what you're really going to be looking into. You're going to have those different possibilities. So you can kind of see how C5H10 having 1 degrees of saturation, it actually gave you a lot of other possibilities of having the constitutional isomers, because as soon as you have 1 degrees of saturation, you can have a ring or a pi bond. So that gives you multiple possibilities there, and you can have the constitutional isomers for the C6H14. If you have any questions, feel free to leave any comments in the section below.